welcome back from lunch. So for your intellectual pleasure and pleasant digestion, our speakers, Marty Flashman, you can read the title and just thank you, Marty.
Thank you. I'm currently visitor at the University of Arizona and have my title emeritus from Humboldt State, which is now called Cal Poly Humboldt. Before I get too far along, I just mention that all the slides that I'm going to show are from GeoGebra. So you can get links to everything that I do, and I have a quick link there on there for you to access it. And I do want to remember mathematicians who I miss a lot. Ruth Favro was my cousin, and I used to often give her a sample presentation so she would help me cut it down to a tolerable time. So if I run over, it's because unfortunately you didn't get a chance to
I'll be here to
give me advice. And David Tall, I used to visit quite regularly in England, and he had a complex analysis book with, he still has one, he doesn't have it, with Ian Stewart, and he was very, enjoyed the work I did, and he actually put some of the, mention and a link to my work in his, in the last edition of this complex book. So, it was a good fun. Yeah, I don't know if this is working, but, so I'm going to try and look at this, and you can look at that, and I'm glad everyone got a seat because it was really crowded earlier. So I'm going to talk about and mainly present visualizations using GeoGebra of complex numbers and functions with mapping diagrams that help illuminate the study of algebra and geometry. So the algebra I'm going to be looking at is visualizing roots of complex quadratic polynomials, and in geometry I'll be visualizing isometries, dilations, and inversions a little bit. And my time may run short because we didn't help me cut it down. Fortunately, there were a couple of talks earlier today. There was a talk on transformation-based geometry and complex numbers, and then later on this afternoon, Frank Farris is going to give a talk on complex numbers in the service of plane geometry. So what I don't get covered, I'll expect them to do a better job. So let me talk a little bit about mapping diagrams, and somebody have something running up. Is that me? I hear something in the background. Okay.
Yeah, something just turned on outer world.
Okay. This is an example of a mapping diagram from the reals to the reals. This is the function minus 2x, and this is the graph of that, and the arrows there indicated the same as the coordinates here. So if you think about 0 goes to 0, then the point 0, 0 divided by goes there. And if you're making a table with these inputs on the left column, in the right column we have the value of the function, and the left axis is for the inputs, and the right axis is for the outputs, and the arrows go from the inputs to the output. In GeoGebra, you can move things around dynamically, so you can see that point moving on the line. And in this thing, I can change this function. I have a list to choose, so that moves up 1. And I can put in quadratic here, and back to the practice. You can see that we have this function is 2 to 1, and you can see that more clearly here in the mapping diagram. We have, for example, minus 2 and 2 are both going to number 4. So that's an example of real mapping diagrams, and what I've done is taken this and transferred this idea to complex analysis and complex functions. And if you want to read this text that goes with many of these slides, I'm just going to go with the pictures in each slide. So here's the traditional mapping diagram that visualizes the squaring function. I can change the functions without any difficulty now. You can see that this circle gets mapped to this cardioid over here. And so there's an input and an output, the separate planes, and we have two separate figures, one for each plane in the mapping diagram. But this is traditionally what appears in most complex analysis books. I don't know any complex analysis book that doesn't have a figure like this. And I have lots of things you can adjust here. For example, I can move this, and you can see how this then gives you the double covering like that. But you can't see, over here it's pretty easy to see which point's going to which, but when I move it here, that kind of information is lost. And one way you can see that is to move something around the circle and you see how it's traced on the other side. Or there are lots of ways that people visualize how the dynamics of what happens on the left corresponds to what happens on the right. But in this figure, you can't see that double covering very easily. You can, of course, if you move this place. That was good. If you move that over.
Do you need that?
Yeah. I'm using it. So we'll see if it comes back on. And if not, hold on. Sorry for the delay. Okay, we're back up. Okay, so that's the first example. That's the old style of mapping diagram. And this is the newer version that I have. So in this diagram, the left hand is sort of a control. It's what, if you were doing reals, you might have a slider. But for complexes, you can't use sliders because they're only real numbers. So this left hand side is my slider. And first I'm going to show you a very simple linear function multiplication by 2. Here's the diagram for it. So you see, if you look at it this way, it looks like a magnification by a factor of 2. And if I had 3D glasses to give you all, I could turn on 3D and you can actually see the 3D illusion here. But I can put a spin on this. Well, anyhow, you can see it spinning around here. And get that 3D. So this is the real axis, and that's the imaginary axis. And just for a quickie, actually, if you think about those arrows as being parts of lines, and you can see that they all read at the same vertex, and I'll leave it for you to figure out why that's true. It's rather trivial that this is a multiplication by this projection. So there's a lot of nice geometry in here related to projections, and even if you're thinking about, one of the reasons why I have my arrows going from up to down is I think topologically is a projection. So projection usually has total space and you project onto the base. Anyhow, that's the example there. We'll take out the lines for a second. And I'll just show you, so that's with A is here, it's 0, so that's, and here's B. And I just want to show you quickly what happens when I move B into the plane. So you can see the rotation there is quite clear. It's a magnification and a rotation. And that's visually much clearer than anything I've seen in the basic mapping diagrams that you have. And you can see that happening in the memory computer. So that's an example of a complex mapping diagram. Anyone have any questions? Feel free to ask them now or later on. And with that, we'll move on to the basic problem here. Now we've seen mathematics and also mapping diagrams. Here's another linear one me to show you this quickly. Actually, I'm going to jump to the quadratics because time is short. Okay, so here's a quadratic. Actually, this is a quick look at z to the n. I went on, I'm sorry. Here's z to the n. And so that's the squaring. You can see the double covering happening in the target here. And you can see both a couple of square roots of 1 and also a couple of square roots of -1. And you can see where they came from, at plus and minus I. I'm going to change this just a little bit. Let's put it up to 3. And so this shows you the three roots of 1 and the 3 roots of -1. And also 3 roots of I and 3 roots of minus I. So this is a visualization of cubics, and I can, if I tip this around, you can actually see it move around 3 times. So there's a lot of nice visualization that can happen dynamically that helps students understand complex analysis, complex functions, I should say. Even if you're in the high school and first encountering complex numbers, you can see a little bit about what they're doing without having to go through the arithmetic of cubing that complex number. So it saves you a lot of time in understanding by not having to do the computational arithmetic to go with it. So now let's look at quadratic equations. So when I look at quadratic equations, here's the ax squared plus bx plus c, but I think about it as being in what I call the composition. People call this the vertex form, but I call it the composition form because in this form, it's a composition of some functions. It's subtract h, then multiply, then square, then multiply by a, then add h. And so in the mapping diagrams, I have subtract 3, square, is that squaring we saw before, then multiply by 2, and then add 1. So this gives the students a way to visualize composition and understand this, completing the square that they talk about, to visualize it all as a composition, and to make sense out of what happens when you solve this equation. So I'm going to take this out for a second, and here's the solution. So here's the number 5. And you can see the question is, when you do this composition, when do you end up at 5? And the solution is, first subtract 1, then divide by 2. Those are inverses. Then find the square root, and then add your 3. And that's how to visualize the solution of that quadratic in a meaningful way. It's not just memorizing the formula, it's understanding the function and understanding what it means to solve the equation. Now, the thing is, of course, that when you change the number that you're trying to solve, now 1.1, it gets a little more challenging. There's only one answer now, and no solutions. But now you have a reason for it. It's not just that the graph doesn't cross the x-axis. You know exactly why it didn't work. It's because you couldn't find that square root. You couldn't reverse the square root for the negative number. And this is where you have to introduce complex numbers and imaginary numbers, and this is a little distressing for the student because there's no visualization for this in the graph of the real plane. But if we've been doing it with mapping diagrams, we can use the mapping diagrams for complex numbers to understand this better. So this looks like this same thing. I'll turn the arrows sideways, and here's the mapping diagram for c minus h, and then this is the rest of the compositions for what I have here. This is 2 times 1 minus z minus 1 minus 1. So I subtracted 1 1, I squared it, multiplied by 2, and then subtract something. Subtract 1. So that's that, and we can see when a is 2, right here, you see these are the coefficients, the parameters in that quadratic from this point. Okay. So I'm going to solve the equation, so I'll take out this thing. Remember how the solution went? So it went same kind of thing we saw before, right? Yeah. And here's my W. It happens to be 1. So we'll change the W. And we see the same thing happening. We get into a problem. Oh, I can't see it anymore. And that's looks like 0. So it's 1. Wait a second, now it's, and you see over here, it's gone into the complex plane. So we see the solutions over here are turning out to be complex numbers. But we don't see them over here, although it says they're there. And the reason we can't see it here is because we're not seeing the whole picture. And this was actually a picture showing the complex. So it was in fact a complex plane that we're looking at, but looking at it head on, so that we only saw the line. And so that illustrates how we can visualize the solution to the complex numbers and see the complex numbers show up here. Okay. Now, so I can multiply with a complex number. All these numbers could be complex. So I move this up. And now you see that the solutions, and we'll just look here for the solutions. The solutions have a symmetry about at one point, but it's not plus or minus a real number, it's plus or minus a complex number. So it's showing it. That's enough. So this is a richer problem. It shows you how that you can solve complex quadratic equations, not just real quadratic equations. So it takes the students into thinking about polynomials with complex coefficients, complex functions, and you can start to talk about polynomials in algebra. I can go full screen. Okay, so this is the same thing, I think. I'm going to skip this. All right, so now let's review quickly some of the geometry of complex arithmetic. So complex addition is vector addition. You see that here. Complex multiplication. This is what it looks like. So complex multiplication. You add the angles and multiply the lengths. And you can write them in here's the R and the theta to go through this. So this is R is 1.7 and the theta is 13. So, and we know that multiply the lengths is the product of these lengths and the angle is the sum of the angles. So people have discussed that already, it's a well-known fact. Let's move on to the inverse, multiplicative inverse. Again, you take the reciprocal of the length and you take the opposite of the angle. So if you really want to take geometrically, this is you're taking the geometric inverse with respect to a unit circle, and then conjugating it, so reflecting across the x-axis. That's the geometry of this, in terms of geometric inversion, which is with respect to the unit circle. So you take the inverse along this line and then reflect it. Okay. So let's take a quick look then. Take a look at some of the. So this is the first thing is here is actually just multiplication by a as a complex number. The number a is 2i, and that's going to give you an amplitwist. And let's put here's the amplitwist. So it's rotated 2i, so it's magnifying by a factor of 2. It's rotating by 90 degrees. And let's take that back over here, and we can see that in this figure here. Let's take this and so over. Let's see over here. There's the amplification, and you can't see the rotation very well in this figure, but you can see the rotation here in the mapping diagram. So that's an amplitwist. Let's do, take this back to where it was, and do rotation. This is rotation with the center at 2, the center rotation, and if we move that over, you can see the rotation a little bit clearly over here. That's a rotation, and the angle of rotation is determined here. So that's rotation, and that's by multiplication by just e to the certain number, and minus the. Oh, yeah, okay. Here's central dilation, and this is dilation by a factor of -2. You can see it over here in the mapping diagram. There's that center of dilation that you see in the geometry, and here's a conjugate x reflection. So that's reflection along the x-axis. That's conjugation. You can see that here. And one quickie here. Move to my last picture here. So this is reflection on the x, but I can also reflect on the y. You can do others, just depending on how you want to compose it. But you can see two reflections that are quite common. And then also I have central inversion. You see a central inversion, which is coming from the conjugate of the complex inverse. So, and here's the mapping diagram for that. It shows it a little bit more clearly how it's inverting. And then if you take that and think of the origin, you see it turns into a line. Okay. So, that brings me to the end. Thanks to the organizers and for you all for finding a seat. And there's my email if you have any questions.
Yeah.
Not a question, but now I understand why you were asking me what software I was using.
Yeah, I don't think this is not easy to do in Mathematica or in Decimals.
Yeah.
I have a question. So, sometimes my students struggle with orientation. How hard would it be to put arrows on the circles
Not hard at all.
to indicate, in the images?
That would be, it's quite easy. But you can solve, you saw that one where I went around these.
Yeah, no, I
So
saw
that
the
showed the
animation
orientation.
too.
But you can put arrows in there, it's quite easy. And see the image.
Did I hear you say that you can wear 3D glasses with
Yeah.
GeoGebra and see some of this?
Yeah, I can show you just quickly. go back down. Let's just go. So, I think this has, go here, and there's a view in here. So, yeah, I'm not seeing it here, but there is a place where you can turn on a 3D view of it all, and that's not showing up here, I guess. There's another place where you, and so it does the 3D, 3 colors, and then you'll see 3D. Another question?
Okay, thank you.
Let's start with our next speaker here, or any